Hello and welcome to another video lecture at mrwatkins.com. This particular video lecture is about calculating oxidation numbers for pre-AP students. So this lesson is really to help pre-AP students understand what oxidation numbers are and how they need to be calculated. It's not really geared towards those that are, say, in a chemistry class. So you need to understand that there's going to be a lot more to this if you're a chemistry student than what I'm presenting here, but this will be basics. So the first thing you need to worry about is that oxidation numbers for oxidation states is the tendency to gain or lose electrons. It's the tendency to gain or lose electrons. Now, it's helpful to have an oxidation number and understanding how this works because it tells you how atoms will interact with each other, how they'll form bonds. And you need to remember that atoms interact, or they form these bonds, with their valence electrons. And in a previous discussion, we've talked about the fact that I want you to consider electrons as being energy. And so when two atoms come together, they're basically sharing an energy piece, sharing those electrons. Sometimes they do donate them and we have what's called an ionic bond, but that's for another lecture. So calculating these things, figuring out what these oxidation numbers are, allows us to make predictions about the behavior of atoms and even about the behavior of a molecule. So it's really important that you understand how to do this in biology because some of these molecules we're going to talk about are really some of the driving forces of how we store energy as we move through the process of cellular respiration and photosynthesis. Let me write down the steps then to calculating oxidation numbers. Step 1, you need to determine the number of valence electrons. So you're going to need a periodic chart for this. And valence electrons are those electrons, and we'll symbolize the electrons with an E with a little line over it, are those electrons found in the outer shell. The second part is you need to apply the octet rule. The octet rule basically is that atoms want to have this full stable shell that has basically 8 electrons in it that are paired together. So, you have 4 pairs or 8 electrons. And then the third step here, you need to determine the charge, determine the number. So you're going to determine what the charge is. And by charge, I'm talking about a positive charge or a negative charge. So determine the charge and then determine the number that that charge is associated with. Such as oxygen's oxidation number is a -2. Negative being the charge, 2 being the number for that negative charge. So let's step through the process here and just do this with oxygen real quick. So oxygen has 8 electrons in the outer, 8 electrons total. How did I know that? Well, oxygen has an atomic number of 8. That means that there are 8 protons in the nucleus of an oxygen molecule. If you change the number of protons in any type of atom, you're going to change that actual atom to a different element. So that's pretty much it. Oxygen, 8 protons. Now, if this is a neutral molecule, in other words, there is no extraneous charge, then that means the number of protons, positive charges, must have the same number of electrons, negative charges. So here we have 8 protons, then we're going to have 8 electrons if this is going to be a neutral atom. Now the thing you need to understand is that this works best if you have an understanding of what's called electron configurations. Now electron configurations are ways of determining where a molecule, where elements are that surround an atom. It's almost like a map, if you will, of in what shell, what orbital, what spot around that nucleus of that atom are these electrons. And it's important to understand electron configuration because valence electrons, these outer electrons, behave in such a way as to help us predict about the function, or at least the reactivity of that particular molecule. So If you want to know about how to do electron configurations, you're going to have to watch the other video. That has a whole separate piece to it. I'm going to make the assumption that you've already seen that video and you understand how to do electron configurations. So when we look at oxygen, its electron configuration is going to be 1s2, 2s2, we've already used up 4 electrons, and 2p4, total of 8 different electrons here. This outer shell, this second shell, it's got 6 electrons in it. 2 of those electrons are in s, and they are paired. So we're going to have 2 of them paired, where one's going to go one direction, one's going to go another. This p orbital, it's got 4 electrons, but as you saw in the other video, this p orbital, if these were the spots where the electrons could be, with 4 of them, we're going to have an electron that spins one direction, another electron that spins one direction, another electron that spins one direction, and then we're going to have an electron that pairs at least with that one. This leaves 2 open spots for electrons to get in. Now, that tells me here, first of all, that we have 6 valence electrons. We're looking at the octet rule, and we're using oxidation number to kind of help us with that particular piece. So with this particular molecule here, we've got 6 electrons in the outer shell. We have a spot for 2. Octet being 8, if you notice, we have a spot for 2. If we were to fill those 2, we would end up picking up, or at least having in the outer shell, 8 total electrons. Now, with oxygen, if it does that, it's going to end up changing the amount of charge that it has as far as negative is concerned. If it were to pick up these extra 2 electrons, these 2 right here, then we're going to add 2 more negative charges. And those 2 negative charges are going to bring our overall negative charge to 10. That means oxygen is going to have a -2 oxidation number. This tells us that oxygen wants to pick up 2 electrons. Now, this is a lot of detail. Let's look at another one, and we're going to look at it in a little more simple fashion. We're going to take nitrogen. So here we're going to have nitrogen. And instead of doing oxidation number this time, I'm just going to run through it step by step with our determining the number of valence electrons, applying this octet rule, and determining the charge and number. Nitrogen has a total number of 7 electrons. Its atomic number is 7, meaning 7 protons, and if it was stable, then it should have 7 electrons. Again, looking back at where electrons can be, 7 total electrons. So 7 total electrons that we have, 2 of those electrons are going to go to that first shell, and that's going to leave us 5 electrons left over. 2 electrons are going to go into that first shell, that 1s2, that first shell, first orbital, leaving us 5 electrons. Those 5 electrons are going to be in the second shell. Now the octet rule says that we want to be at 8, or we want, get rid of those 8. So let me ask this, is 5 electrons, is it easier for these 5 to be removed from this nitrogen? Or is it easier to gain 3 electrons so that we now have 8? All I did was subtract 5 from 8. So which would have less energy? Which would take less energy? Well, it would take less energy to pick up 3 electrons than to try to move 5. So if we picked up 3 electrons here, if we added in 3 electrons, we no longer had 7 electrons. We now have 10 electrons. We have 7 protons because our atomic number is 7, but we have 10 electrons. The difference here is those 3 electrons that get added. So nitrogen's oxidation number is going to be a -3. And what this tells us, again, is that for nitrogen, it wants to have 3 electrons. And it will form bonds, or at least 3 bonds, to help fulfill that. Let's look at the electron configuration again here, just so we can keep some consistency and kind of see what's going on. 1s2, 2 electrons, first shell, that first orbital. It leaves 5 left over. 2s2, we had 5. We're going to fill that second shell, that s orbital with those two, and then we still have some left over. We've got 3 left over, and we're going to have 2p3. And remember, in that p orbital, there's 3 places for electrons. We first have to fill in each spot before we can add any to it. And when you look at that, that means, or when we look at this, you can see that there is an empty spot, 3 empty spots here in this shell, in that particular orbital, that can take electrons. Okay, we're going to do another one here. This time we're going to use hydrogen as the example. And so let's have a look at what hydrogen will do. Hydrogen is kind of special. Hydrogen has an atomic number of 1. And because it has 1 proton, and if it's a neutral atom, then it's going to have 1 electron. So as we look here, we're going to have that 1 electron in 1s1. Now, with hydrogen being a rather interesting molecule, very, very important to biological systems, that 1s electron, that 1 electron, according to a octet rule, you're either going to want to get rid of that 1 electron, or you're going to have to add in 7 electrons so that you now have an outer shell of 8. Hydrogen cannot handle having that many electrons, and certainly it takes less energy just to get rid of 1 than to pick up 7, and that's what ends up happening. So this 1 electron disappears, that leaves 1 proton. This time we have 1 more positive charge than negative charges. So hydrogen will carry a +1 charge. Let's go back to our oxygen. Oxygen, remember, has 8 electrons. 2 go into the first shell, and that leaves us 6 in the next shell, in that second shell. Octet rule says we want to be at 8 or 0. It's easier to pick up those 2 electrons, and so oxygen has a -2 oxidation number. Now here's the interesting piece. If you look at this, oxygen has a spot for 2 electrons. Hydrogen wants to give away the electrons. If you look carefully here, you can see if this hydrogen gives away its electrons to satisfy this oxygen, the oxygen isn't satisfied. It needs 1 more electron for it to be satisfied. If another hydrogen ion comes in, oxidation numbers again of +1, and it puts that 1 electron, gives that over, or shares that over with oxygen, we now have oxygen satisfied. Oxygen cannot take just, or is not satisfied with just having the 1 hydrogen. It actually takes 2. This is why water is such an important molecule in biological systems. So is oxygen. We're going to find later that this hydrogen ion is incredibly important in setting up a concentration gradient so that our cells can do work. And they use this property of water, where we have our hydrogen ions fulfilling and satisfying the needs of the oxygen molecule or oxygen atom, so that we can then use that to do things like cellular respiration and break down those sugars that you eat. I hope you've had a good idea, or get a good idea about how to calculate oxidation numbers. There's also a lesson that you can walk through, and please don't forget there is a electron configuration video that you can watch so that you can understand what I'm talking about here when I talk about 1s1 and 2s1 and those kind of things. Thank you.